CHAPTER 6 Database Design. Using the ER model up to this point in the text, we have assumed a given database schema and studied how queries and updates are expressed. We now consider how to design a database schema in the first place. In this chapter, we focus on the Entity Relationship Data Model, ER, which provides a means of identifying entities to be represented in the database and how those entities are related. Ultimately, the database design will be expressed in terms of a relational database design and an associated set of constraints. We show in this chapter how honor design can be transformed into a set of relation schemas and how some of the constraints can be captured in that design. Then, in Chapter 7, we consider in detail whether a set of relation schemas is a good or bad database design and study the process of creating good designs using a broader set of constraints. These two chapters cover the fundamental concepts of database design. 6.1 Overview of the design process. The task of creating a database application is a complex one, involving design of the database schema, design of the programs that access and update the data, and design of a security scheme to control access to data. The needs of the users play a central role in the design process. In this chapter, we focus on the design of the database schema, although we briefly outline some of the other design tasks later in the chapter. 6.1.1 Design Phases. For small applications, it may be feasible for a database designer who understands the application requirements to decide directly on the relations to be created, their attributes, and constraints on the relations. However, such a direct design process is difficult for real-world applications, since they are often highly complex. Often no one person understands the complete data needs of an application. The database designer must interact with users of the application to understand the needs of the application, represent them in a high-level fashion that can be understood by the users, and 241. 242 Chapter 6 Database Design. Using the ER model, then translate the requirements into lower levels of the design. A high-level data model serves the database designer by providing a conceptual framework in which to specify, in a systematic fashion, the data requirements of the database users, and a database structure that fulfills these requirements. The initial phase of database design is to characterize fully the data needs of the prospective database users. The database designer needs to interact extensively with domain experts and users to carry out this task. The outcome of this phase is a specification of user requirements. While there are techniques for diagrammatically representing user requirements, in this chapter we restrict ourselves to textual descriptions of user requirements. Next, the designer chooses a data model and, by applying the concepts of the chosen data model, translates these requirements into a conceptual schema of the database. The schema developed at this conceptual design phase provides a detailed overview of the enterprise. The entity relationship model, which we study in the rest of this chapter, is typically used to represent the conceptual design. Stated in terms of the entity relationship model, the conceptual schema specifies the entities that are represented in the database, the attributes of the entities, the relationships among the entities, and constraints on the entities and relationships. Typically, the conceptual design phase results in the creation of an entity relationship diagram that provides a graphic representation of the schema. The designer reviews the schema to confirm that all data requirements are indeed satisfied and are not in conflict with one another. She can also examine the design to remove any redundant features. Her focus at this point is on describing the data and their relationships, rather than on specifying physical storage details. A fully developed conceptual schema also indicates the functional requirements of the enterprise. In a specification of functional requirements, users describe the kinds of operations, or transactions, that will be performed on the data. Example operations include modifying or updating data, searching for and retrieving specific data, and deleting data. At this stage of conceptual design, the designer can review the schema to ensure that it meets functional requirements. The process of moving from an abstract data model to the implementation of the database proceeds in two final design phases. Degree in the logical design phase, the designer maps the high-level conceptual schema onto the implementation data model of the database system that will be used. The implementation data model is typically the relational data model, and this step typically consists of mapping the conceptual schema defined using the entity relationship model into a relation schema. Finally, the designer uses the resulting system-specific database schema in the subsequent physical design phase, in which the physical features of the database. 6.1 Overview of the design process 243 are specified. These features include the form of file organization and choice of index structures, discussed in Chapter 13 and Chapter 14. The physical schema of a database can be changed relatively easily after an application has been built. However, changes to the logical schema are usually harder to carry out, since they may affect a number of queries and updates scattered across application code. It is therefore important to carry out the database design phase with care, before building the rest of the database application. 6.1.2 Design alternatives. A major part of the database design process is deciding how to represent in the design the various types of things such as people, places, products, and the like. We use the term entity to refer to any such distinctly identifiable item. In a university database, examples of entities would include instructors, students, departments, courses, and course offerings. We assume that a course may have run in multiple semesters, as well as multiple times in a semester. We refer to each such offering of a course as a section. The various entities are related to each other in a variety of ways, all of which need to be captured in the database design. For example, a student takes a course offering, while an instructor teaches a course offering. Teaches and takes are examples of relationships between entities. In designing a database schema, we must ensure that we avoid two major pitfalls. 1. Redundancy. A bad design may repeat information. For example, if we store the course identifier and title of a course with each course offering, the title would be stored redundantly, i.e., multiple times, unnecessarily, with each course offering. It would suffice to store only the course identifier with each course offering, and to associate the title with the course identifier only once, in a course entity. Redundancy can also occur in a relational schema. In the university example we have used so far, we have a relation with section information and a separate relation with course information. Suppose that instead we have a single relation where we repeat all of the course information, course ID, title, dep name, credits, once for each section, offering, of the course. Information about courses would then be stored redundantly. The biggest problem with such redundant representation of information is that the copies of a piece of information can become inconsistent if the information is updated without taking precautions to update all copies of the information. For example, different offerings of a course may have the same course identifier, but may have different titles. It would then become unclear what the correct title of the course is. Ideally, information should appear in exactly one place. 2. Incompleteness. A bad design may make certain aspects of the enterprise difficult or impossible to model. For example, suppose that, as in case 1, above, we only had entities corresponding to course offering, without having an entity. 244 6.2 Chapter 6 Database Design using the ER model corresponding to courses. Equivalently, in terms of relations, suppose we have a single relation where we repeat all of the course information once for each section that the course is offered. It would then be impossible to represent information about a new course, unless that course is offered. We might try to make do with the problematic design by storing null values for the section information. Such a workaround is not only unattractive but may be prevented by primary key constraints. Avoiding bad designs is not enough. There may be a large number of good designs from which we must choose. As a simple example, consider a customer who buys a product. Is the sale of this product a relationship between the customer and the product? Alternatively, is the sale itself an entity that is related both to the customer and to the product? This choice, though simple, may make an important difference in what aspects of the enterprise can be modeled well. Considering the need to make choices such as this for the large number of entities and relationships in a real-world enterprise, it is not hard to see that database design can be a challenging problem. Indeed, we shall see that it requires a combination of both science and good taste. The Entity Relationship Model. The Entity Relationship, ER, data model was developed to facilitate database design by allowing specification of an enterprise schema that represents the overall logical structure of a database. Their model is very useful in mapping the meanings and interactions of real-world enterprises onto a conceptual schema. Because of this usefulness, many database design tools draw on concepts from their model. Their data model employs three basic concepts: entity sets, relationship sets, and attributes. Their model also has an associated diagrammatic representation, their diagram. As we saw briefly in section 1.3.1, Honor diagram can express the overall logical structure of a database graphically. Their diagrams are simple and clear qualities that may well account in large part for the widespread use of their model. The Tools section at the end of the chapter provides information about several diagram editors that you can use to create your diagrams. 6.2.1 Entity sets. An entity is a thing or object in the real world that is distinguishable from all other objects. For example, each person in a university is an entity. An entity has a set of properties, and the values for some set of properties must uniquely identify an entity. For instance, a person may have a personid property whose value uniquely identifies that person. Thus, the value 677-89-9011 for personid would uniquely identify one particular person in the university. Similarly, courses can be thought of as entities, and course E uniquely identifies a course entity in the university. An entity may be concrete, such. 6.2 The entity relationship model 245 as a person or a book, or it may be abstract, such as a course offering, or a flight reservation. An entity set is a set of entities of the same type that share the same properties, or attributes. The set of all people who are instructors at a given university, for exam PLE, can be defined as the entity set instructor. Similarly, the entity set student might represent the set of all students in the university. In the process of modeling, we often use the term entity set in the abstract, without referring to a particular set of individual entities. We use the term extension of the entity set to refer to the actual collection of entities belonging to the entity set. Thus, the set of actual instructors in the university forms the extension of the entity set instructor. This distinction is similar to the difference between a relation and a relation instance, which we saw in Chapter 2. Entity sets do not need to be disjoint. For example, it is possible to define the entity set person consisting of all people in a university. A person entity may be an instructor entity, a student entity, both, or neither. An entity is represented by a set of attributes. Attributes are descriptive properties possessed by each member of an entity set. The designation of an attribute for an entity set expresses that the database stores similar information concerning each entity in the entity set. However, each entity may have its own value for each attribute. Possible attributes of the instructor entity set are ID name, dep name, and salary. In real life, there would be further attributes, such as street number, apartment number, state, postal code, and country, but we generally omit them to keep our examples simple. Possible attributes of the course entity set are course title, dep name, and credits. In this section we consider only attributes that are simple, those not divided into subparts. In section 6.3, we discuss more complex situations where attributes can be composite and multivalued. Each entity has a value for each of its attributes. For instance, a particular instructor entity may have the value 12,121 for ID, the value WU for name, the value finance for dep name, and the value 90,000 for salary. The ID attribute is used to identify instructors uniquely, since there may be more than one instructor with the same name. Historically, many enterprises found it convenient to use a government-issued identification number as an attribute whose value uniquely identifies the person. However, that is considered bad practice for reasons of security and privacy. In general, the enterprise would have to create and assign its own unique identifier for each instructor. A database thus includes a collection of entity sets, each of which contains any number of entities of the same type. A database for a university may include a number of other entity sets. For example, in addition to keeping track of instructors and students, the university also has information about courses, which are represented by the entity set course with attribute courseid title dep name and credits. In a real setting, a university database may keep dozens of entity sets. An entity set is represented in honor diagram by a rectangle, which is divided into two parts. The first part, which in this text is shaded blue, contains the name of 246 Chapter 6 Database Design using the ER model Instructor ID Name Salary Student ID Name Taught _cred Figure 6.1 Ear diagram showing entity sets Instructor round Student. The entity set. The second part contains the names of all the attributes of the entity set. The ear diagram in Figure 6.1 shows two entity sets Instructor round Student. The attributes associated with Instructor ID Name, and Salary. The attributes associated with Student ID Name, and Tocred. Attributes that are part of the primary key are underlined, see Section 6.5. 6.2.2 Relationship sets a relationship in association among several entities. For example, we can define a relationship advisor hat associates instructor Katz with student Shankar. This relationship specifies that Katz is an advisor to student Shankar. A relationship set is a set of relationships of the same type. Consider two entity sets instructor round student. We define the relationship seat advisor to denote the associations between students and the instructors who act as their advisors. Figure 6.2 depicts this association. To keep the figure simple, only some of the attributes of the two entity sets are shown. A relationship instance on a schema represents an association between the named entities in the real-world enterprise that is being modeled. As an illustration, the individual instructor entity Katz, who has instructor ID 45565, and the student entity Shankar, who has student ID 12345, participate in a relationship instance OFAD v76766 CRIC 45565 Katz 10101 Srinivasan 98345 Kim 76543 Singh 22222 Einstein Instructor 98988 Tanaka 12345 Shankar 00128 Jong 76543 Brown 76653 Aoi 23121 Chavez 44553 Peltier Student Figure 6.2 Relationship Seat Advisor. Only some attributes of instructor round student are shown. 6.2 The Entity Relationship Model 247 Instructor ID Name Salary Student ID Name Taught _cred Advisor Figure 6.3 Ear diagram showing Relationship Seat Advisor. SOR. This relationship instance represents that in the university, the instructor Katz is advising student Shankar. A relationship set is represented in honor diagram by Adiamond, which is linked via Linesto a number of different entity sets, rectangles. The ear diagram in Figure 6.3 shows the two entity sets instructor round student, related through a binary relationship seat advisor. As another example, consider the two entity set student and section, where section denotes an offering of a course. We can define the relationship set ACUS to denote the association between a student and a section in which that student is enrolled. Although in the preceding examples each relationship set was an association between two entity sets, in general a relationship set may denote the association of more than two entity sets. Formally, a relationship set is a mathematical relation on greater than or equal to two, possibly non-distinct, entity sets. If at 1 E2, E-ner entity sets, then a relationship set RIS a subset of E1 E2, En, E1 set membership symbol E1 E2 set membership symbol E2, En set membership symbol En where E1 E2, En is a relationship instance. The association between entity sets is referred to as participation, i.e., the entity sets E1 E2, En participate in relationship set R. The function that an entity plays in a relationship is called that entity's role. Since entity sets participating in a relationship set are generally distinct, roles are implicit and are not usually specified. However, they are useful when the meaning of a relationship needs clarification. Such is the case when the entity sets of a relationship set are not distinct, that is, the same entity set participates in a relationship set more than once, in different roles. In this type of relationship set, sometimes called a recursive relationship set, explicit role names are necessary to specify how an entity participates in a relationship instance. For example, consider the entity set course author records information about all the courses offered in the university. To depict the situation where one course, C2, is a prerequisite for another course, C1, we have relationship set prereq that is modeled by ordered pairs of course entities. The first course of a pair takes the role of course C1, whereas the second takes the role of prerequisite course C2. In this way, all relationships of prereq are characterized by C1, C2, pairs, C2, C1, pairs are excluded. We indicate roles in ear diagrams by labeling the lines that connect diamonds. 248 Chapter 6 Database Design Using the ER Model Course ID prereq ID course ID Title Credits Prereq Figure 6.4 Ear Diagram with Role Indicators. To rectangles. Figure 6.4 shows the role indicators course and prereq between the course entity set and the prereq relationship set. A relationship may also have attributes called descriptive attributes. As an example of descriptive attributes for relationships, consider the relationship set which relates entity set student and section. We may wish to store a descriptive attribute grade with the relationship to record the grade that a student received in a course offering. An attribute of a relationship set is represented in honor diagram by an undivided rectangle. We link the rectangle with a dashed line to the diamond representing that relationship set. For example, Figure 6.5 shows the relationship set between the entity set section and student. We have the descriptive attribute a grade tagged to the relationship set X. A relationship set may have multiple descriptive attributes. For example, we may also store a descriptive attribute for credit with the relationship set to record whether a student has taken the section for credit, or is auditing, or sitting in on, the course. Observe that the attributes of the two entity sets have been omitted from the ER diagram in Figure 6.5, with the understanding that they are specified elsewhere in the complete ER diagram for the university. We have already seen the attributes for student, and we will see the attributes of section later in this chapter. Complex redesigns may need to be split into multiple diagrams that may be located in different pages. Relationship sets should be shown in only one location, but entity sets may be repeated in more than one location. The attributes of an entity set should be shown in the first OC occurrence. Subsequent occurrences of the entity set should be shown without attributes, to avoid repetition of information and the resultant possibility of inconsistency in the attributes shown in different occurrences. Grade Student section takes Figure 6.5 ER diagram with an attribute attached to a relationship set. 6.3 Complex Attributes 249 6.3 It is possible to have more than one relationship set involving the same entity sets. For example, suppose that students may be teaching assistants for a course. Then, the entity set section and student may participate in a relationship set teaching assistant, in addition to participating in the relationship set. The formal definition of a relationship set, which we saw earlier, defines a relationship set as a set of relationship instances. Consider the relationship between student and section. Since a set cannot have duplicates, it follows that a particular student can have only one association with a particular section in the relationship. Thus, a student can have only one grade associated with a section, which makes sense in this case. However, if we wish to allow a student to have more than one grade for the same section, we need to have an attribute a grades which stores a set of grades. Such attributes are called multivalued attributes, and we shall see them later in section 6.3. The relationship sets advisoran provide examples of a binary relationship set, that is, one that involves two entity sets. Most of the relationship sets in a database system are binary. Occasionally, however, relationship sets involve more than two entity sets. The number of entity sets that participate in a relationship set is the degree of the relationship set. A binary relationship set is of degree 2, a ternary relationship set is of degree 3. As an example, suppose that we have an entity set project that represents all the research projects carried out in the university. Consider the entity sets instructor, student, and project. Each project can have multiple associated students and multiple associated instructors. Furthermore, each student working on a project must have an associated instructor who guides the student on the project. For now, we ignore the first two relationships between project and instructor, and between project and student. Instead, we focus on the information about which instructor is guiding which student on a particular project. To represent this information, we relate the three entity sets through a ternary relationship set project guide, which relates entity sets instructor, student, and project. An instance of project guide A indicates that a particular student is guided by a particular instructor on a particular project. Note that a student could have different instructors as guides for different projects, which cannot be captured by a binary relationship between students and instructors. Non-binary relationship sets can be specified easily in honor diagram. Figure 6.6 shows the diagram representation of the ternary relationship set project guide. Complex attributes. For each attribute, there is a set of permitted values, called the domain, or value set, of that attribute. The domain of attribute Korth might be the set of all text strings of a certain length. Similarly, the domain of attributes Mr might be strings from the set fall, winter, spring, summer. 250 Chapter 6 Database Design using the ER model. Instructor ID name, salary, student ID name, taught _cred proj _guide project. Figure 6.6 ear diagram with a ternary relationship project guide. Name, address, composite attributes, first _name, middle _initial, last _name, street, city, state, postal _code, component attributes, street _number, street _name, apartment _number. Figure 6.7 Composite attributes, instructor name and address. An attribute, as used in their model, can be characterized by the following attribute types. Simplene composite attributes. In our examples thus far, the attributes have been simple, that is, they have not been divided into subparts. Composite attributes, on the other hand, can be divided into subparts, i.e., other attributes. For example, an attribute name could be structured as a composite attribute consisting of first name, middle initial, and last name. Using composite attributes in a design schema is a good choice if a user will wish to refer to an entire attribute on some occasions, and to only a component of the attribute on other occasions. Suppose we were to add an address to the student entity set. The address can be defined as the composite attribute address with the attributes street, city, state, and postal code. Point 1 Composite attributes help us to group together related attributes, making the modeling cleaner. Note also that a composite attribute may appear as a hierarchy. In the composite attribute address, its component attribute a street can be further divided into street number, street name, and apartment number. Figure 6.7 depicts these examples of composite attributes for the instructor entity set. 1. We assume the address format used in the United States, which includes a numeric postal code called a zip code. 6.3 Complex attributes 251 single-valued and multi-valued attributes. The attributes in our examples all have a single value for a particular entity. For instance, the student ID attribute for a specific student entity refers to only one student ID. Such attributes are said to be single-valued. There may be instances where an attribute has a set of values for a specific entity. Suppose we add to the instructor entity set a phone number attribute. An instructor may have 0, 1, or several phone numbers, and different instructors may have different numbers of phones. This type of attribute is said to be multi-valued. As another example, we could add to the instructor entity set an attribute dependent name listing all the dependents. This attribute would be multi-valued, since any particular instructor may have 0, 1, or more dependents. Derived attributes. The value for this type of attribute can be derived from the values of other related attributes or entities. For instance, let us say that the instructor entity set has an attribute as students advised, which represents how many students an instructor advises. We can derive the value for this attribute by counting the number of student entities associated with that instructor. As another example, suppose that the instructor entity set has an attribute age that indicates the instructor's age. If the instructor entity set also has an attribute date of birth, we can calculate ega from date of birth and the current date. Thus, age is a derived attribute. In this case, date of birth may be referred to as a base attribute, or asterisk attribute. The value of a derived attribute is not stored but is computed when required. Figure 6.8 shows how composite attributes can be represented in their notation. Here, a composite attribute name with component attribute as first name, middle initial, and last name replaces the simple attribute name of instructor. As another example, suppose we were to add an address to the instructor entity set. The address can be defined as the composite attribute address with the attributes street, city, state, and postal code. The attribute street is itself a composite attribute whose component attributes are street number, street name, and department number. The figure also illustrates a multi-valued attribute phone number, denoted by phone number, and a derived attribute age, depicted by age. An attribute takes a null value when an entity does not have a value for it. The null value may indicate not applicable, that is, the value does not exist for the entity. For example, a person who has no middle name may have the middle initial attribute set to null. Null can also designate that an attribute value is unknown. An unknown value may be either missing, the value does exist, but we do not have that information, or not known, we do not know whether or not the value actually exists. For instance, if the name value for a particular instructor is null, we assume that the value is missing, since every instructor must have a name. A null value for the apartment number attribute could mean that the address does not include an apartment number, not applicable, that an apartment number exists but we do not know what. 252 Chapter 6 Database Design using the ER model. Instructor ID name first underscore name middle underscore initial last underscore name address street underscore number street underscore name apt underscore number city state zip phone underscore number date underscore of underscore birth age. 6.4 Figure 6.8 EAR diagram with composite, multivalued, and derived attributes. It is missing, or that we do not know whether or not an apartment number is part of the instructor's address, unknown. Mapping cardinalities. Mapping cardinalities, or cardinality ratios, express the number of entities to which another entity can be associated via a relationship set. Mapping cardinalities are most useful in describing binary relationship sets, although they can contribute to the description of relationship sets that involve more than two entity sets. For a binary relationship set or between entity sets on B, the mapping cardinality must be one of the following: 1-to-1. An entity in A is associated with that mistone A entity in B, and an entity in B is associated with that mistone A entity INA. See Figure 6.9a. 1-to-many. An entity in A is associated with any number, 0 or more, of entities in B. An entity in B, however, can be associated with that mistone A entity INA. See Figure 6.9b. Many-to-one. An entity in A is associated with that mistone A entity in B. An entity in B, however, can be associated with any number, 0 or more, of entities INA. See Figure 6.10a. 6.4 Mapping cardinalities. 253, A, B, A, B, A1, A2, A3, B1, B2, B3, B4, B5, A, B, A1, A2, A3, A4, B1, B2, B3. Figure 6.9 Mapping cardinalities. A, 1-to-1. B, 1-to-many. Many-to-many. An entity in A is associated with any number, 0 or more, of entities in B, and an entity in B is associated with any number, 0 or more, of entities INA. See Figure 6.10b. The appropriate mapping cardinality for a particular relationship set obviously depends on the real-world situation that the relationship set is modeling. As an illustration, consider the advisor relationship set. If a student can be advised by several instructors, as in the case of students advised jointly, the relationship set is many-to-many. In contrast, if a particular university imposes a constraint that a student can be advised by only one instructor, and an instructor can advise several students, then the relationship set from instructor to student must be 1-to-many. Thus, Mapping AB A1 2 A 2 A3 A4 A5 B1 B2 B3 B1 B2 B3 B4 A1 A2 A3 A4 A, B, Figure 6.10 Mapping cardinality ties. A, many to one. B, many to many. 254 Chapter 6 Database Design Using the ER model. Cardinality ties can be used to specify constraints on what relationships are permitted in the real world. In their diagram notation, we indicate cardinality constraints on a relationship by drawing either a directed line, rightward arrow, or an indirect line, between the relationship set and the entity set in question. Specifically, for the university example, 1-to-1. We draw a directed line from the relationship set to both entity sets. For example, in Figure 6.11a, the directed lines to instructor and student indicate that an instructor may advise at most one student, and a student may have at most one advisor. Advisor instructor ID name salary student ID name taught _cred, A, 1-to-1 advisor instructor ID name salary student ID name taught _cred, B, 1-to-many advisor instructor ID name salary student ID name taught _cred, C, many-to-one advisor instructor ID name salary student ID name taught _cred, D, many-to-many. Figure 6.11 Relationship cardinality ties. 6.4 Mapping cardinality ties. 255 1-to-many. We draw a directed line from the relationship set to the one side of the relationship. Thus, in Figure 6.11b, there is a directed line from relationship set advisor to the entity set instructor, and an indirect line to the entity set student. This indicates that an instructor may advise many students, but a student may have at most one advisor. Many-to-one. We draw a directed line from the relationship set to the one side of the relationship. Thus, in Figure 6.11c, there is an indirect line from the relationship set advisor to the entity set instructor and a directed line to the entity set student. This indicates that an instructor may advise at most one student, but a student may have many advisors. Many-to-many. We draw an indirect line from the relationship set to both entity sets. Thus, in Figure 6.11d, there are indirect lines from the relationship set advisor to both entity sets instructor and student. This indicates that an instructor may advise many students, and a student may have many advisors. The participation of an entity set in a relationship set is said to be total if every entity in E must participate in at least one relationship in R. If it is possible that some entities in do not participate in relationships in R, the participation of entity set in relationship is said to be partial. For example, a university may require every student to have at least one advisor. In their model, this corresponds to requiring each entity to be related to at least one instructor through the advisor relationship. Therefore, the participation of student in the relationship set advisor is total. In contrast, an instructor need not advise any students. Hence, it is possible that only some of the instructor entities are related to the student entity set through the advisor relationship, and the participation of instructor in the advisor relationship set is therefore partial. We indicate total participation of an entity in a relationship set using double lines. Figure 6.12 shows an example of the advisor relationship set where the double line indicates that a student must have an advisor. Ear diagrams also provide a way to indicate more complex constraints on the number of times each entity participates in relationships in a relationship set. A line may have an associated minimum and maximum cardinality, shown in the form L. H. Where instructor ID name salary student ID name taught _cred advisor. Figure 6.12 Ear diagram showing total participation. 256 Chapter 6 Database Design Using the ER Model Instructor 0. ID name salary 11 student ID name taught _cred advisor. Figure 6.13 Cardinality limits on relationship sets. Is the minimum nth maximum cardinality. A minimum value of 1 indicates total participation of the entity set in the relationship set, that is, each entity in the entity set occurs in at least one relationship in that relationship set. A maximum value of 1 indicates that the entity participates in at most one relationship, while a maximum value indicates no limit. For example, consider Figure 6.13. The line between advisor and student is a cardinality constraint of 1. 1, meaning the minimum and the maximum cardinality are both 1. That is, each student must have exactly one advisor. The limit 0. On the line between advisor and instructor indicates that an instructor can have 0 or more students. Thus, the relationship advisories one-to-many from instructor to student, and further the participation of student in advisories total, implying that a student must have an advisor. It is easy to misinterpret the 0 on the left edge and think that the relationship advisories many to one from instructor to student. This is exactly the reverse of the correct interpretation. If both edges have a maximum value of 1, the relationship is 1 to 1. If we had specified a cardinality limit of 1 on the left edge, we would be saying that each instructor must advise at least one student. The diagram in figure 6.13 could alternatively have been drawn with a double line from student to advisor, and an arrow on the line from advisor to instructor, in place of the cardinality constraints shown. This alternative diagram would enforce exactly the same constraints as the constraints shown in the figure. In the case of non-binary relationship sets, we can specify some types of many-to-one relationships. Suppose a student can have at most one instructor as a guide on a project. This constraint can be specified by an arrow pointing to instructor on the edge from project guide. We permit at most one arrow out of a non-binary relationship set, since on our diagram with two or more arrows out of a non-binary relationship set can be interpreted in two ways. We elaborate on this issue in section 6.5.2. Primary key. We must have a way to specify how entities within a given entity set and relationships within a given relationship set are distinguished. 6.5 6.5 Primary key 257 6.5.1 Entity sets. Conceptually, individual entities are distinct. From a database perspective, however, the differences among them must be expressed in terms of their attributes. Therefore, the values of the attribute values of an entity must be such that they can uniquely identify the entity. In other words, no two entities in an entity set are allowed to have exactly the same value for all attributes. The notion of a key for a relation schema, as defined in section 2.3, applies directly to entity sets. That is, a key for an entity is a set of attributes that suffice to distinguish entities from each other. The concepts of superkey, candidate key, and primary key are applicable to entity sets just as they are applicable to relation schemas. Keys also help to identify relationships uniquely, and thus distinguish relationships from each other. Next, we define the corresponding notions of keys for relationship sets. 6.5.2 Relationship sets. We need a mechanism to distinguish among the various relationships of a relationship set. Let R be a relationship set involving entity sets E1, E2, En. Let primary key, EI, denote the set of attributes that forms the primary key for entity set EI. Assume for now that the attribute names of all primary keys are unique. The composition of the primary key for a relationship set depends on the set of attributes associated with the relationship set R. If the relationship set has no attributes associated with it, then the set of attributes primary key, E1, union set symbol primary key, E2, union set symbol primary key, En, describes an individual relationship in set R. If the relationship set has attributes A1, A2, associated with it, then the set of attributes primary key, E1, union set symbol primary key, E2, union set symbol primary key, En, union set symbol A1, A2, AM describes an individual relationship in set R. If the attribute names of primary keys are not unique across entity sets, the attributes are renamed to distinguish them. The name of the entity set combined with the name of the attribute would form a unique name. If an entity set participates more than once in a relationship set, as in the prereq relationship in section 6.2.2, the role name is used instead of the name of the entity set, to form a unique attribute name. Recall that a relationship set is a set of relationship instances, and each instance is uniquely identified by the entities that participate in it. Thus, in both of the preceding cases, the set of attributes primary key, E1, union set symbol primary key, E2, union set symbol primary key, En, forms a superkey for the relationship set. 258 Chapter 6 Database Design Using the ER Model. The choice of the primary key for a binary relationship set depends on the mapping cardinality of the relationship set. For many-to-many relationships, the preceding union of the primary keys is a minimal superkey and is chosen as the primary key. As an illustration, consider the entity sets instructor and student, and the relationship seat advisor, in section 6.2.2. Suppose that the relationship set is many-to-many. Then the primary key of advisor consists of the union of the primary keys of instructor and student. For one-to-many and many-to-one relationships, the primary key of the many side is a minimal superkey and is used as the primary key. For example, if the relationship is many-to-one from student to instructor, that is, each student can have at most one advisor, then the primary key of advisor is simply the primary key of student. However, if an instructor can advise only one student, that is, if the advisor relationship is many-to-one from instructor to student, then the primary key of advisor is simply the primary key of instructor. For one-to-one relationships, the primary key of either one of the participating entity sets forms a minimal superkey, and either one can be chosen as the primary key of the relationship set. However, if an instructor can advise only one student, and each student can be advised by only one instructor, that is, if the advisor relationship is one-to-one, then the primary key of either student or instructor can be chosen as the primary key for advisor. For non-binary relationships, if no cardinality constraints are present, then the superkey formed as described earlier in this section is the only candidate key, and it is chosen as the primary key. The choice of the primary key is more complicated if cardinality constraints are present. As we noted in section 6.4, we permit at most one arrow out of a relationship set. We do so because an diagram with two or more arrows out of a non-binary relationship set can be interpreted in the two ways we describe below. Suppose there is a relationship set between entity sets E1, E2, E3, E4, and the only arrows are on the edges to entity sets E3 and 4. Then, the two possible interpretations are: 1. A particular combination of entities from E1, E2 can be associated with at most one combination of entities from E3, E4. Thus, the primary key for the relationship can be constructed by the union of the primary keys of E1 and 2. 2. A particular combination of entities from E1, E2, E3 can be associated with at most one combination of entities from E4, and further a particular combination of entities from E1, E2, E4 can be associated with at most one combination of entities from E3, then the union of the primary keys of E1, E2, and 3 forms a candidate key, as does the union of the primary keys of E1, E2, and 4. Each of these interpretations has been used in practice and both are correct for particular enterprises being modeled. Thus, to avoid confusion, we permit only one arrow out of a non-binary relationship set, in which case the two interpretations are equivalent. 6.5 Primary key 259. In order to represent a situation where one of the multiple arrow situations holds, their design can be modified by replacing the non-binary relationship set with an entity set. That is, we treat each instance of the non-binary relationship set as an entity. Then we can relate each of those entities to corresponding instances of E1, E2, E4 via separate relationship sets. A simpler approach is to use functional dependencies, which we study in Chapter 7, Section 7.4. Functional dependencies which allow either of these interpretations to be specified simply in an unambiguous manner. The primary key for the relationship set is then the union of the primary keys of those participating entity sets if that do not have an incoming arrow from the relationship set R. 6.5.3 Weak entity sets. Consider a section entity, which is uniquely identified by a course identifier, semester, year, and section identifier. Section entities are related to course entities. Suppose we create a relationship set course between entity set section and course. Now, observe that the information in course is redundant, since section already has an attribute courseid, which identifies the course with which the section is related. One option to deal with this redundancy is to get rid of the relationship course. However, by doing so the relationship between section and course becomes implicit in an attribute, which is not desirable. An alternative way to deal with this redundancy is to not store the attribute course in the section entity and to only store the remaining attributes ESED year and semester. Point 2. However, the entity set section then does not have enough attributes to identify a particular section entity uniquely. Although each section entity is distinct, sections for different courses may share the same ESED year and semester. To deal with this problem, we treat the relationship course as a special relationship that provides extra information, in this case the course ED, required to identify section entities uniquely. The notion of weak entity set formalizes the above intuition. A weak entity set is one whose existence is dependent on another entity set, called its identifying entity set. Instead of associating a primary key with a weak entity, we use the primary key of the identifying entity, along with extra attributes, called discriminator attributes to uniquely identify a weak entity. An entity set that is not a weak entity set is termed a strong entity set. Every weak entity must be associated with an identifying entity, that is, the weak entity set is said to be existence dependent in the identifying entity set. The identifying entity set is said to be weak entity set that it identifies. The relationship associating the weak entity set with the identifying entity set is called the identifying relationship. The identifying relationship is many-to-one from the weak entity set to the identifying entity set, and the participation of the weak entity set in the relationship is total. To note that the relational schema we eventually create from the entity set section does have the attribute course ED, for reasons that will become clear later, even though we have dropped the attribute course ED from the entity set section. 260 Chapter 6 Database Design. Using the ER model, the identifying relationship set should not have any descriptive attributes, since any such attributes can instead be associated with the weak entity set. In our example, the identifying entity set for section is course, and the relationship set course, which associates section entities with their corresponding course entities, is the identifying relationship. The primary key of section is formed by the primary key of the identifying entity set, that is course, plus the discriminator of the weak entity set, that is section. Thus, the primary key is course ID ESED year semester. Note that we could have chosen to make ESED globally unique across all courses offered in the university, in which case the section entity set would have had a primary key. However, conceptually, a section is still dependent on a course for its existence, which is made explicit by making it a weak entity set. In near diagrams, a weak entity set is depicted via a double rectangle with the discriminator being underlined with a dashed line. The relationship set connecting the weak entity set to the identifying strong entity set is depicted by a double diamond. In Figure 6.14, the weak entity set section depends on the strong entity set course via the relationship set course. The figure also illustrates the use of double lines to indicate that the participation of the weak entity set section in the relationship course is total, meaning that every section must be related via course to some course. Finally, the arrow from course to course indicates that each section is related to a single course. In general, a weak entity set must have a total participation in its identifying relationship set, and the relationship is many-to-one toward the identifying entity set. A weak entity set can participate in relationships other than the identifying relationship. For instance, the section entity could participate in a relationship with the time-slot entity set, identifying the time when a particular class section meets. A weak entity set may participate as owner in an identifying relationship with another weak entity set. It is also possible to have a weak entity set with more than one identifying entity set. A particular weak entity would then be identified by a combination of entities, one from each identifying entity set. The primary key of the weak entity set would consist of the union of the primary keys of the identifying entity sets, plus the discriminator of the weak entity set. Course_ID title credits section SEC_ID semester year SEC_course Figure 6.14 ear diagram with a weak entity set. 6.6 Removing redundant attributes in entity sets 261 6.6 Removing redundant attributes in entity sets. When we design a database using the ER model, we usually start by identifying those entity sets that should be included. For example, in the university organization we have discussed thus far, we decided to include such entity sets as student and instructor. Once the entity sets are decided upon, we must choose the appropriate attributes. These attributes are supposed to represent the various values we want to capture in the database. In the university organization, we decided that for the instructor entity set, we will include the attributes ID name, dep name, and salary. We could have added the attribute as phone number, office number, homepage, and others. The choice of what attributes to include is up to the designer, who has a good understanding of the structure of the enterprise. Once the entities and their corresponding attributes are chosen, the relationship sets among the various entities are formed. These relationship sets may result in a situation where attributes in the various entity sets are redundant and need to be removed from the original entity sets. To illustrate, consider the entity sets instructor and department. The entity set instructor includes the attributes ID name, dep name, and salary, with ID forming the primary key. The entity set department includes the attribute as dep name, building, and budget, with dep name forming the primary key. We model the fact that each instructor has an associated department using a relationship set inst dep relating instructor and department. The attribute dep name appears in both entity sets. Since it is the primary key for the entity set department, it is redundant in the entity set instructor and needs to be removed. Removing the attribute dep name from the instructor entity set may appear rather unintuitive, since the relation instructor that we used in the earlier chapters had an attribute dep name. As we shall see later, when we create a relational schema from the ear diagram, the attribute dep name in fact gets added to the relation instructor, but only if each instructor has at most one associated department. If an instructor has more than one associated department, the relationship between instructors and departments is recorded in a separate relation inst dept. Treating the connection between instructors and departments uniformly as a relationship, rather than as an attribute of instructor, makes the logical relationship explicit, and it helps avoid a premature assumption that each instructor is associated with only one department. Similarly, the student entity set is related to the department entity set through the relationship set student dept, and thus there is no need for a dep name attribute in student. 262 Chapter 6 Database Design using the ER model as another example. Consider course offerings, sections, along with the time slots of the offerings. Each time slot is identified by a time s-loaded, and has associated with it a set of weekly meetings, each identified by a day of the week, start time, and end time. We decide to model the set of weekly meeting times as a multivalued composite attribute. Suppose we model entity set section end time slot as follows. The entity set section includes the attribute as courseid semester year building room number, and time s-loaded, with courseid year semester, forming the primary key. The entity set time s-load includes the attribute as time s-loaded, which is the primary key 3 and a multivalued composite attribute, day start time end time. Point 4. These entities are related through the relationship set sec time s-lot. The attribute at time s-load appears in both entity sets. Since it is the primary key for the entity set time s-lot, it is redundant in the entity set section and needs to be removed. As a final example, suppose we have an entity set classroom, with attributes building, room number, and capacity, with building gondroom number forming the primary key. Suppose also that we have a relationship set class hat relate section ta classroom. Then the attributes building room number are redundant in the entity set section. A good entity relationship design does not contain redundant attributes. For our university example, we list the entity sets and their attributes below, with primary keys underlined, classroom, with attributes, building, room number capacity. Department, with attributes, dep name building budget. Course, with attributes, courseid title credits. Instructor, with attributes, ID name salary. Section, with attributes, courseid, sysid, semester year. Student, with attributes, ID name tocred. Time slot, with attributes, time slotted, day start time end time. The relationship sets in our design are listed below, inst dept, relating instructors with departments. Studept, relating students with departments. 3. We shall see later on that the primary key for the relation created from the entity set time s-load includes day and start time. however day and start to do not form part of the primary key of the entity set time slot. 4. We could optionally give a name, such as meeting, for the composite attribute containing day start time, on end time. 6.6 Removing redundant attributes in entity sets. 263 teaches, relating instructors with sections. Takes, relating students with sections, with a descriptive attribute grade. Course adept, relating courses with departments. Secours, relating sections with courses. SEC/LAS, relating sections with classrooms. SecTime slot, relating sections with time slots. Advisor, relating students with instructors. Prereq, relating courses with prerequisite courses. You can verify that none of the entity sets has any attribute that is made redundant by one of the relationship sets. Further, you can verify that all the information, other than constraints, in the relational schema for our university database, which we saw earlier in Figure 2.9, has been captured by the above design, but with several attributes in the relational design replaced by relationships in their design. We are finally in a position to show, Figure 6.15, their diagram that corresponds to the university enterprise that we have been using thus far in the text. This diagram is equivalent to the textual description of the university model, but with several additional constraints. In our university database, we have a constraint that each instructor must have exactly one associated department. As a result, there is a double line in Figure 6.15 between instructor and inst-dept, indicating total participation of instructor in inst-dept, that is, each instructor must be associated with a department. Further, there is an AR row from inst-dept to department, indicating that each instructor can have at most one associated department. Similarly, entity set course has a double line to relationship set course adept, indicating that every course must be in some department. An entity set student has a double line to relationship set adept, indicating that every student must be majoring in some department. In each case, an arrow points to the entity set department to show that a course, and, respectively, a student, can be related to only one department, not several. Similarly, entity set course has a double line to relationship set course adept, indicating that every course must be in some department. An entity set student is a double line to relationship set adept, indicating that every student must be majoring in some department. In each case, an arrow points to the entity set department to show that a course, and, respectively, a student, can be related to only one department, not several. Further, Figure 6.15 shows that the relationship set has a descriptive attribute grade, and that each student has at most one advisor. The figure also shows that section is a weak entity set, with attributes ESID semester, and IR forming the discriminator. Secours size the identifying relationship set relating weak entity set section to the strong entity set course. 264 Chapter 6 Database Design Using the ER Model Student ID Name tot_cred time_slot_ID Day start_time End_time course_ID Takes Instructor ID Name Salary SEC_course_ID Title Credits Prereq_ID Advisor Section SEC_ID Semester Year Teaches Prereq INST_department_name Building Budget course_department SEC_class SEC_time_slot grade stud_department classroom building room_number capacity 6.7 Figure 6.15 Ear diagram for a university enterprise. In section 6.7, we show how these diagram can be used to derive the various relation schemas we use. Reducing ER diagrams to relational schemas. Both their model and the relational database model are abstract, logical representations of real-world enterprises. Because the two models employ similar design principles, we can convert honor design into a relational design. For each entity set and for each relationship set in the database design, there is a unique relation schema to which we assign the name of the corresponding entity set or relationship set. 6.7 Reducing ER diagrams to relational schemas. 265 In this section, we describe how honor schema can be represented by relation schemas and how constraints arising from their design can be mapped to constraints on relation schemas. 6.7.1 Representation of strong entity sets. Let E be a strong entity set with only simple descriptive attributes A1 A2, AN. We represent this entity with a schema called with distinct attributes. Each tuple in a relation on this schema corresponds to one entity of the entity set E. For schemas derived from strong entity sets, the primary key of the entity set serves as the primary key of the resulting schema. This follows directly from the fact that each tuple corresponds to a specific entity in the entity set. As an illustration, consider the entity set student of their diagram in figure 6.15. This entity set has three attributes: ID, name, tokrid. We represent this entity set by a schema called student with three attributes: student, ID, name, tokrid. Note that since student ID is the primary key of the entity set, it is also the primary key of the relation schema. Continuing with our example, for their diagram in figure 6.15, all the strong entity sets, except time slot, have only simple attributes. The schemas derived from these strong entity sets are depicted in figure 6.16. Note that the instructor, student, and course schemas are different from the schemas we have used in the previous chapters. They do not contain the attribute dep name. We shall revisit this issue shortly. 6.7.2 Representation of strong entity sets with complex attributes. When a strong entity set has non-simple attributes, things are a bit more complex. We handle composite attributes by creating a separate attribute for each of the component attributes. We do not create a separate attribute for the composite attribute itself. To illustrate, consider the version of the instructor entity set depicted in figure 6.8. For the composite attribute name, the schema generated for instructor contains the attributes classroom, building, room number, capacity, department, dep name, building budget, course, course-side title, credits, instructor, ID name, salary, student, ID name, tokrid. Figure 6.16 schemas derived from the entity sets in their diagram in figure 6.15. 266 Chapter 6 Database Design using the ER model. First name, middle initial, and last name. There is no separate attribute or schema for name. Similarly, for the composite attribute address, the schema generated contains the attributes street, city, state, and postal code. Since street is a composite attribute, it is replaced by street number, street name, and app number. Multivalued attributes are treated differently from other attributes. We have seen that attributes in honor diagram generally map directly into attributes for the appropriate relation schemas. Multivalued attributes, however, are an exception. New relation schemas are created for these attributes, as we shall see shortly. Derived attributes are not explicitly represented in the relational data model. However, they can be represented as stored procedures, functions, or methods in other data models. The relational schema derived from the version of entity set instructor with complex attributes, without including the multivalued attribute, is thus: instructor, ID, first name, middle initial, last name, street number, street name, app number, city, state, postal code, date of birth. For a multivalued attribute M, we create a relation schema with an attribute A that corresponds to M and D attributes corresponding to the primary key of the entity set or relationship set of which miss an attribute. As an illustration, consider their diagram in figure 6.8 that depicts the entity set instructor, which includes the multivalued attribute Tiffany number. The primary key of instructor is ID. For this multivalued attribute, we create a relation schema instructor phone, ID phone number. Each phone number of an instructor is represented as a unique tuple in the relation on this schema. Thus, if we had an instructor with ID 22222, and phone numbers 555, 1234 and 555, 4321, the relation instructor phone would have two tuples, 22,222, 555, 1234, and 22,222, 555, 4321. We create a primary key of the relation schema consisting of all attributes of the schema. In the above example, the primary key consists of both attributes of the relation schema instructor phone. In addition, we create a foreign key constraint on the relation schema created from the multivalued attribute. In that newly created schema, the attribute generated from the primary key of the entity set must reference the relation generated from the entity set. In the above example, the foreign key constraint on the instructor-phoner relation would be that attribute references the instructor relation. In the case that an entity set consists of only two attributes, a single primary key attribute and a single multivalued attribute M, the relation schema for the entity set would contain only one attribute, namely, the primary key attribute B. We can drop 6.7 Reducing ER diagrams to relational schemas 267 This relation, while retaining the relation schema with the attribute band attribute A that corresponds to. To illustrate, consider the entity set time slot depicted in figure 6.15. Here time slot ED is the primary key of the time slot entity set, and there is a single multivalued attribute that happens also to be composite. The entity set can be represented by just the following schema created from the multivalued composite attribute, time slotted day, start time, end time. Although not represented as a constraint on their diagram, we know that there cannot be two meetings of a class that start at the same time of the same day of the week but end at different times. Based on this constraint, end time has been omitted from the primary key of the time slot schema. The relation created from the entity set would have only a single attribute time slotted. The optimization of dropping this relation has the benefit of simplifying the resultant database schema, although it has a drawback related to foreign keys, which we briefly discuss in section 6.7.4. 6.7.3 Representation of weak entity sets. Let A be a weak entity set with attributes A1 A2, AM. Let B be the strong entity set on which A depends. Let the primary key of B consist of attribute A1 B2, Bn. We represent the entity set A by a relation schema called A1 attribute for each member of the set, A1 A2, AM union set symbol B1 B2, Bn for schemas derived from a weak entity set. The combination of the primary key of the strong entity set and the discriminator of the weak entity set serves as the primary key of the schema. In addition to creating a primary key, we also create a foreign key constraint on the relation, specifying that the attribute A1 B2, Bn reference the primary key of the relation B. The foreign key constraint ensures that for each tuple representing a weak entity, there is a corresponding tuple representing the corresponding strong entity. As an illustration, consider the weak entity set section in their diagram of figure 6.15. This entity set has the attributes SID semester, and year. The primary key of the course entity set, on which section depends, is courseid. Thus, we represent section by a schema with the following attributes: section, courseid, SID, semester, year. The primary key consists of the primary key of the entity set course, along with the discriminator of section, which is SID semester, and year. We also create a foreign key. 268 Chapter 6 Database Design using the ER model constraint on the section schema, with the attribute courseid referencing the primary key of the course schema. 56.7.4 Representation of relationship sets. Let R be a relationship set. Let A1 A2, AM be the set of attributes formed by the union of the primary keys of each of the entity sets participating I and R, and let the descriptive attributes, if any, of RB1 B2, Bn. We represent this relationship set by a relation schema called R with one attribute for each member of the set, A1 A2, AM union set symbol B1 B2, Bn. We described in section 6.5, how to choose a primary key for a binary relationship set. The primary key attributes of the relationship set are also used as the primary key attributes of the relational schema R. As an illustration, consider the relationship seat advisor in their diagram of figure 6.15. This relationship set involves the following entity sets: instructor, with the primary key ID; student, with the primary key ID. Since the relationship set has no attributes, the advisor schema has two attributes: the primary keys of instructor and student. Since both attributes have the same name, we are named Themi and SID. Since the advisor relationship set is many-to-one from student to instructor, the primary key for the advisor relation schema is SID. We also create foreign key constraints on the relation schema R as follows: for each entity set E related by relationship set R, we create a foreign key constraint from relation schema R, with the attributes of RTAT were derived from primary key attributes of ER referencing the primary key of the relation schema representing I. Returning to our earlier example, we thus create two foreign key constraints on the advisor relation, with attribute EI referencing the primary key of instructor round. Attribute side referencing the primary key of student. Applying the preceding techniques to the other relationship sets in their diagram in Figure 6.15, we get the relational schemas depicted in Figure 6.17. Observe that for the case of the relationship set prereq, the role indicators associated with the relationship are used as attribute names, since both roles refer to the same relation course. Similar to the case of advisor, the primary key for each of the relation set course, sectime slot SEC las inst depth studept, and course adept consists of the primary key 5 optionally. The foreign key constraint could have an on-delete cascade specification, so that deletion of a course entity automatically deletes an ejection entities that reference the course entity. Without that specification, each section of a course would have to be deleted before the corresponding course can be deleted. 6.7 Reducing ER diagrams to relational schemas 269 teaches, ID, course-id, CSID, semester year, takes, ID, course-id, CSID, semester year grade, prereq, course-id prerequisite, advisor, SID IID, SECourse, course-id, CSID, semester year, sectime slot, course-id, CSID, semester year time slotted, SEC las, course-id, CSID, semester year building room number, inst dept, ID dept name, studept, ID dept name, course adept, course-id dept name. Figure 6.17 schemas derived from relationship sets in their diagram in Figure 6.15. Of only one of the two related entity sets, since each of the corresponding relationships is many to one. Foreign keys are not shown in Figure 6.17, but for each of the relations in the figure there are two foreign key constraints, referencing the two relations created from the two related entity sets. Thus, for example, SECourse has foreign keys referencing section and classroom teach esha's foreign keys referencing instructor round section, and take sha's foreign keys referencing student and section. The optimization that allowed us to create only a single relation schema from the entity setime slot, which had a multivalued attribute, prevents the creation of a foreign key from the relation schema sectime slot of the relation created from entity setime slot. Since we dropped the relation created from the entity setime slot, we retained the relation created from the multivalued attribute and named it time slot, but this relation may potentially have no tuples corresponding to a time sloted, or it may have multiple tuples corresponding to a time sloted, thus time slotted and sectime slot cannot reference this relation. The astute reader may wonder why we have not seen the schema SECourse SEC time slot SEC las inst depth studept, and course adept in the previous chapters. The reason is that the algorithm we have presented thus far results in some schemas that can be either eliminated or combined with other schemas. We explore this issue next. 6.7.5 Redundancy of schemas. A relationship set linking a weak entity set to the corresponding strong entity set is treated specially. As we noted in section 6.5.3, these relationships are many to one and have no descriptive attributes. Furthermore, the of a weak entity set includes the primary key of the strong entity set. In their diagram of Figure 6.14, the weak entity set sect ion is dependent on the strong entity set course via the relationship set SECourse. 270 Chapter 6 Database Design. Using the ER model, the primary key of section is course-id CSID semester year and the primary key of course-I course-id. Since SECourse has no descriptive attributes, the SECourse schema has attributes course-id CSID semester and year. The schema for the entity set section includes the attributes course-id CSID semester and year, among others. Every course-id CSID semester year combination in a SECourse relation would also be present in the relation on schema section, and vice versa. Thus, the SECourse schema is redundant. In general, the schema for the relationship set linking a weak entity set to its corresponding strong entity set is redundant and does not need to be present in a relational database design based upon honor diagram. 6.7.6 Combination of schemas. Consider a many-to-one relationship set A from entity set A to entity set B. Using our relational schema construction algorithm outlined previously, we get three schemas A, B, and AB. Suppose further that the participation of and the relationship is total, that is, every entity A in the entity C must participate in the relationship AB. Then we can combine the schemas OND AB to form a single schema consisting of the union of attributes of both schemas. The primary key of the combined schema is the primary key of the entity set into whose schema the relationship set schema was merged. To illustrate, let's examine the various relations in the diagram of figure 6.15 that satisfy the preceding criteria. Inst dept. The schemas instructor and department correspond to the entity sets A and B, respectively. Thus, the schema inst dept can be combined with the instructor schema. The resulting instructor schema consists of the attributes ID name, department name, salary. St-dept. The schema student and department correspond to the entity sets A and B, respectively. Thus, the schema st-dept can be combined with the student schema. The resulting student schema consists of the attributes ID name, department name, tokrid. Korth-dept. The schemas course A and department correspond to the entity sets A and B, respectively. Thus, the schema source-dept can be combined with the course schema. The resulting course schema consists of the attributes course-id title, department name, credits. SECC-LAS. The schema section and classroom correspond to the entity sets OND B, respectively. Thus, the schema C-class can be combined with the section schema. The resulting section schema consists of the attributes course-id SISID semester, year, building room number. Sec-time slot. The schema section and time slot correspond to the entity sets OND respectively, thus, the schema sec-time slot can be combined with the section. 6.8 Extended ER features 271 6.8 schema obtained in the previous step. The resulting section schema consists of the attributes course-id SISID semester, year, building room number, times loaded. In the case of one-to-one relationships, the relation schema for the relationship set can be combined with the schemas for either of the entity sets. We can combine schemas even if the participation is partial by using null values. In the preceding example, if inst dept were partial, then we would store null values for the dept name attribute for those instructors who have no associated department. Finally, we consider the foreign key constraints that would have appeared in the schema representing the relationship set. There would have been foreign key constraints referencing each of the entity sets participating in the relationship set. We drop the constraint referencing the entity set into whose schema the relationship set schema is merged, and add the other foreign key constraints to the combined schema. For example, inst dept is a foreign key constraint of the attribute dept name referencing the department relation. This foreign constraint is enforced implicitly by the instructor relation when the schema for inst dept is merged into instructor. Extended ER features. Although the base ISR concepts can model most database features, some aspects of a database may be more aptly expressed by certain extensions to the base ISR model. In this section, we discuss the extended features of specialization, generalization, higher and lower level entity sets, attribute inheritance, and aggregation. To help with the discussions, we shall use a slightly more elaborate database schema for the university. In particular, we shall model the various people within a university by defining an entity set person, with attributes ID name, street, and city. 6.8.1 Specialization. An entity set may include subgroupings of entities that are distinct in some way from other entities in the set. For instance, a subset of entities within an entity set may have attributes that are not shared by all the entities in the entity set. Their model provides a means for representing these distinctive entity groupings. As an example, the entity set person may be further classified as one of the following: employee, student. Each of these person types is described by a set of attributes that includes all the attributes of entity set person plus possibly additional attributes. For example, employee entities may be described further by the attribute salary, whereas student entities may. 272 Chapter 6 Database Design using the ER model be described further by the attribute tokrid. The process of designating subgroupings within an entity set is called specialization. The specialization of person allows us to distinguish among person entities according to whether they correspond to employees or students. In general, a person could be an employee, a student, both, or neither. As another example, suppose the university divides students into two categories, graduate and undergraduate. Graduate students have an office assigned to them. Undergraduate students are assigned to a residential college. Each of these student types is described by a set of attributes that includes all the attributes of the entity set student plus additional attributes. We can apply specialization repeatedly to refine a design. The university could create two specializations of student, namely graduate and undergraduate. As we saw earlier, student entities are described by the attributes ID, name, street, city, and TOE cred. The entity set graduate would have all the attributes of student and an additional attribute office number. The entity set undergraduate would have all the attributes of student, and an additional attribute a residential college. As another example, university employees may be further classified as one of instructor or secretary. Each of these employee types is described by a set of attributes that includes all the attributes of entity set employee plus additional attributes. For example, instructor entities may be described further by the attribute rank, while secretary entities are described by the attribute Horspear week. Further, secretary entities may participate in a relationship secretary for between the secretary and employee entity sets, which identifies the employees who are assisted by a secretary. An entity set may be specialized by more than one distinguishing feature. In our example, the distinguishing feature among employee entities is the job the employee performs. Another, coexistent, specialization could be based on whether the person is a temporary, limited term, employee or a permanent employee, resulting in the entity set's temporary employee and permanent employee. When more than one specialization is formed on an entity set, a particular entity may belong to multiple specializations. For instance, a given employee may be a temporary employee who is a secretary. In terms of honor diagram, specialization is depicted by a hollow arrowhead pointing from the specialized entity to the other entity, see figure 6.18. We refer to this relationship as the IS relationship, which stands for is a and represents, for example, that an instructor is an employee. The way we depict specialization in honor diagram depends on whether an entity may belong to multiple specialized entity sets or if it must belong to at most one specialized entity set. The former case, multiple sets permitted, is called overlapping specialization, while the latter case, at most one permitted, is called disjoint specialization. For an overlapping specialization, as is the case for student and employee as specializations of person, two separate arrows are used. For a disjoint specialization, as is the case for instructor and secretary as specializations of employee, a single arrow is used. The specialization relationship may also be referred to as a superclass-subclass relationship. Higher and lower level entity sets are depicted as regular entity sets, that is, as rectangles containing the name of the entity set. 6.8 Extended ER features 273, Person ID, Name, Street, City, Employee, Salary, Student, Taught _ Credits, Instructor, Rank, Secretary, Hours _ per _ week. Figure 6.18 Specialization and Generalization. 6.8.2 Generalization. The refinement from an initial entity set into successive levels of entity subgroupings represents a top-down design process in which distinctions are made explicit. The design process may also proceed in a bottom-up manner, in which multiple entity sets are synthesized into a higher-level entity set on the basis of common features. The database designer may have first identified instructor entity set with attribute as instructor id, instructor name, instructor salary, and rank. Secretary entity set with attribute secretary id, secretary name, secretary salary, and hours per week. There are similarities between the instructor entity set and the secretary entity set in the sense that they have several attributes that are conceptually the same across the two entity sets, namely, the identifier, name, and salary attributes. This commonality can be expressed by generalization, which is a containment relationship that exists between a higher-level entity set and one or more lower-level entity sets. In our example, employee is the higher-level entity set and instructor and secretary are lower-level entity sets. In this case, attributes that are conceptually the same had different names in the two lower-level entity sets. To create a generalization, the attributes must be given a common name and represented with the higher-level entity person. We can use the attribute names ID, name street, and city, as we saw in the example in section 6.8.1. 274 Chapter 6 Database Design Using the ER model. Higher and lower level entity sets also may be designated by the terms superclass and subclass, respectively. The person entity set is the superclass of the employee and student subclasses. For all practical purposes, generalization is a simple inversion of specialization. We apply both processes, in combination, in the course of designing the ER schema for an enterprise. In terms of the diagram itself, we do not distinguish between specialization and generalization. New levels of entity representation are distinguished, specialization, or synthesized, generalization, as the design schema comes to express fully the database application and the user requirements of the database. Differences in the two approaches may be characterized by their starting point and overall goal. Specialization stems from a single entity set. It emphasizes differences among entities within the set by creating distinct lower-level entity sets. These lower-level entity sets may have attributes, or may participate in relationships, that do not apply to all the entities in the higher-level entity set. Indeed, the reason a designer applies specialization is to represent such distinctive features. If student and employee have exactly the same attributes as person entities, and participate in exactly the same relationships as person entities, there would be no need to specialize the person entity set. Generalization proceeds from the recognition that a number of entity sets share some common features, namely, they are described by the same attributes and participate in the same relationship sets. On the basis of their commonalities, generalization synthesizes these entity sets into a single, higher-level entity set. Generalization is used to emphasize the similarities among lower-level entity sets and to hide the differences. It also permits an economy of representation in that shared attributes are not repeated. 6.8.3 Attribute inheritance. A crucial property of the higher and lower level entities created by specialization and generalization is attribute inheritance. The attributes of the higher level entity sets are said to be inherited by the lower level entity sets. For example, student and employee inherit the attributes of person. Thus student is described by its ID, name, street, and city attributes, and additionally acclaimed attribute, employee is described by its ID, name, street, and city attributes, and additionally ancillary attribute. Attribute inheritance applies through all tiers of lower-level entity sets, thus instructor and secretary, which are subclasses of employee, inherit the attributes ID, name, street, and city from person, in addition to inheriting salary from employee. A lower-level entity set, or subclass, also inherits participation in the relationship sets in which its higher-level entity, or superclass, participates. Like attribute inheritance, participation inheritance applies through all tiers of lower-level entity sets. For example, suppose the person entity set participates in a relationship person depth with department. Then, the student employee instructor and secretary entity sets, which are subclasses of the person entity set, also implicitly participate in the person depth relationship with department. These entity sets can participate in any relationships in which the person entity set participates. 6.8 Extended ER features. 275 Whether a given portion of honor model was arrived at by specialization or generalization, the outcome is basically the same, a higher-level entity set with attributes and relationships that apply to all of its lower-level entity sets. Lower-level entity sets with distinctive features that apply only within a particular lower-level entity set. In what follows, although we often refer to only generalization, the properties that we discuss belong fully to both processes. Figure 6.18 depicts a hierarchy of entity sets. In the figure, employee is a lower-level entity set of person and a higher-level entity set of the instructor and secretary entity sets. In a hierarchy, a given entity set may be involved as a lower-level entity set in only one IS relationship, that is, entity sets in this diagram have only single inheritance. If an entity set is a lower-level entity set in more than one IS relationship, then the entity set has multiple inheritance, and the resulting structure is said to be alitas. 6.8.4 Constraints on specializations. To model an enterprise more accurately, the database designer may choose to place certain constraints on a particular generalization/specialization. One type of constraint on specialization which we saw earlier specifies whether a specialization is disjoint or overlapping. Another type of constraint on a specialization/generalization is a completeness constraint, which specifies whether or not an entity in the higher-level entity set must belong to at least one of the lower-level entity sets within the generalization/specialization. This constraint may be one of the following: total specialization or generalization. Each higher-level entity must belong to a lower-level entity set. Partial specialization or generalization. Some higher-level entities may not belong to any lower-level entity set. Partial specialization is the default. We can specify total specialization in honor diagram by adding the keyword total in the diagram and drawing a dashed line from the keyword to the corresponding hollow arrowhead to which it applies, for a total specialization, or to the set of hollow arrowheads to which it applies, for an overlapping specialization. The specialization of percentage student or employee is total if the university does not need to represent any person who is neither a student nor an employee. However, if the university needs to represent such persons, then the specialization would be partial. The completeness and disjointness constraints do not depend on each other. Thus, specializations may be partial overlapping, partial disjoint, total overlapping, and total disjoint. 276 Chapter 6 Database Design. Using the ER model, we can see that certain insertion and deletion requirements follow from the constraints that apply to a given generalization or specialization. For instance, when a total completeness constraint is in place, an entity inserted into a higher-level entity set must also be inserted into at least one of the lower-level entity sets. An entity that is deleted from a higher-level entity set must also be deleted from all the associated lower-level entity sets to which it belongs. 6.8.5 Aggregation. One limitation of their model is that it cannot express relationships among relationships. To illustrate the need for such a construct, consider the ternary relationship PROJ guide, which we saw earlier, between an instructor, student and project, see Figure 6.6. Now suppose that each instructor guiding a student on a project is required to file a monthly evaluation report. We model the evaluation report as an entity evaluation, with a primary key evaluation id. One alternative for recording the student project instructor combination to which an evaluation corresponds is to create a quaternary, four-way relationship seed-eval for between instructor-student project and valuation. A quaternary relationship is required. A binary relationship between student and evaluation, for example, would not permit us to represent the project instructor combination to which an evaluation corresponds. Using the basis remodeling constructs, we obtain the diagram of Figure 6.19. We have omitted the attributes of the entity sets, for simplicity. It appears that the relationship sets project ID and eval for can be combined into one single relationship set. Nevertheless, we should not combine them into a single instructor project student eval underscore for PROJ underscore guide evaluation. Figure 6.19 ear diagram with redundant relationships. 6.8 Extended ER features. 277 Project PROJ underscore guide instructor student eval underscore for evaluation. Figure 6.20 ear diagram with aggregation relationship. Since some instructor-student project combinations may not have an associate evaluation, there is redundant information in the resultant figure. However, since every instructor-student project combination in eval for must also be in project guide. If evaluation was modeled as a value rather than an entity, we could instead make evaluation a multi-valued composite attribute of the relationship set project guide. However, this alternative may not be an option if an evaluation may also be related to other entities. For example, each evaluation report may be associated with a secretary who is responsible for further processing of the evaluation report to make scholarship payments. The best way to model a situation such as the one just described is to use aggregation. Aggregation is an abstraction through which relationships are treated as higher-level entities. Thus, for our example, we regard the relationship set project guide, relating the entity sets instructor student, and project, as a higher level entity set called project guide. Such an entity set is treated in the same manner as is any other entity set. We can then create a binary relationship eval for between project guide and evaluation to represent which student project instructor combination and evaluation is for. Figure 6.20 shows a notation for aggregation commonly used to represent this situation. 6.8.6 Reduction to relation schemas. We are in a position now to describe how the extended features can be translated into relation schemas. 278 Chapter 6 Database Design using the ER Model. 6.8.6.1 Representation of generalization. There are two different methods of designing relation schemas for honor diagram that includes generalization. Although we refer to the generalization in Figure 6.18 in this discussion, we simplify it by including only the first tier of lower-level entity sets, that is employee and student. We assume that it is the primary key of person. 1. Create a schema for the higher-level entity set. For each lower-level entity set, create a schema that includes an attribute for each of the attributes of that entity set plus 1 for each attribute of the primary key of the higher-level entity set. Thus, for the diagram of Figure 6.18, ignoring the instructor and secretary entity sets, we have three schemas: person, ID name, street, city, employee, ID salary, student, ID tokrid. The primary key attributes of the higher-level entity set become primary key attributes of the higher-level entity set as well as all lower-level entity sets. These can be seen underlined in the preceding example. In addition, we create foreign key constraints on the lower-level entity sets, with their primary key attributes referencing the primary key of the relation created from the higher-level entity set. In the preceding example, the ID attribute of employee would reference the primary key of person, and similarly for student. 2. An alternative representation is possible, if the generalization is disjoint and complete, that is, if no entity is a member of two lower-level entity sets directly below a higher-level entity set, and if every entity in the higher-level entity set is also a member of one of the lower-level entity sets. Here, we do not create a schema for the higher-level entity set. Instead, for each lower-level entity set, we create a schema that includes an attribute for each of the attributes of that entity set plus 1 for each attribute of the higher-level entity set. Then, for the diagram of Figure 6.18, we have two schemas: employee, ID name, street, city, salary, student, ID name, street, city, tokrid. Both these schemas have ID, which is the primary key attribute of the higher-level entity set person, as their primary key. One drawback of the second method lies in defining foreign key constraints. To illustrate the problem, suppose we have a relationship set involving entity set person. With the first method, when we create a relation schema from the relationship set, we also define a foreign key constraint on R, referencing the schema person. Unfortunately, with the second method, we do not have a single relation to which a foreign key. 6.9 Entity Relationship Design Issues 279 6.9 Constraint on R can refer. To avoid this problem, we need to create a relation schema person containing at least the primary key attributes of the person entity. If the second method were used for an overlapping generalization, some values would be stored multiple times, unnecessarily. For instance, if a person is both an employee and a student, values for street and city would be stored twice. If the generalization were disjoint but not complete, that is, if some person is neither an employee nor a student, then an extra schema person, ID name, street, city, would be required to represent such people. However, the problem with foreign key constraints mentioned above would remain. As an attempt to work around the problem, suppose employees and students are additionally represented in the person relation. Unfortunately, name, street, and city information would then be stored redundantly in the person relation and the student relation for students, and similarly in the person relation and the employee relation for employees. That suggests storing name, street, and city information only in the person relation and removing that information from student and employee. If we do that, the result is exactly the first method we presented. 6.8.6.2 Representation of aggregation. Designing schemas for honor diagram containing aggregation is straightforward. Consider figure 6.20. The schema for the relationship seed eval for between the aggregation of project ID and the entity seed evaluation includes an attribute for each attribute in the primary keys of the entity seed evaluation and the relationship set project guide. It also includes an attribute for any descriptive attributes, if they exist, of the relationship set eval for. We then transform the relationship sets and entity sets within the aggregated entity set following the rules we have already defined. The rules we saw earlier for creating primary key and foreign key constraints on relationship sets can be applied to relationship sets involving aggregations as well, with the aggregation treated like any other entity set. The primary key of the aggregation is the primary key of its defining relationship set. No separate relation is required to represent the aggregation, the relation created from the defining relationship is used instead. Entity relationship design issues. The notions of an entity set and a relationship set are not precise, and it is possible to define a set of entities and the relationships among them in a number of different ways. In this section, we examine basic issues in the design of honor database schema. Section 6.11 covers the design process in further detail. 280 Chapter 6 Database Design using the ER model. Stud department student ID name taught _ cred department _ name department _ name building budget. A. Incorrect use of attribute assignment marks student section stud _ section. B. Erroneous use of relationship attributes. Figure 6.21 Example of erroneous diagrams. 6.9.1 Common mistakes in ER diagrams. A common mistake when creating ER models is the use of the primary key of an entity set as an attribute of another entity set, instead of using a relationship. For example, in our university ER model, it is incorrect to have dep name as an attribute of student, as depicted in figure 6.21a. Even though it is present as an attribute in the relation schema for student. The relationship stdep is the correct way to represent this information in the ER model, since it makes the relationship between student and department explicit, rather than implicit via an attribute. Having an attribute dep name as well as a relationship stdep would result in duplication of information. Another related mistake that people sometimes make is to designate the primary key attributes of the related entity sets as attributes of the relationship set. For example, ID, the primary key attributes of student, and ID, the primary key of instructor, should not appear as attributes of the relationship advisor. This should not be done since the primary key attributes are already implicit in the relationship set. 6a Third common mistake is to use a relationship with a single valued attribute in a situation that requires a multi-valued attribute. For example, suppose we decided to represent the marks that a student gets in different assignments of a course offering section. A wrong way of doing this would be to add two attributes assignment and marks to the relationship takes, as depicted in figure 6.21b. The problem with this design is that we can only represent a single assignment for a given student section pair. 6 When we create a relation schema from the ER schema, the attributes may appear in a schema created from the advisor relationship set, as we shall see later. However, they should not appear in the advisor relationship set. 6.9 Entity Relationship Design Issues 281 Assignment SEC_assign section marks student marks _in. C. Correct alternative to erroneous ER diagram. B. Assignment _marks assignment marks student section stud _section. D. Correct alternative to erroneous ER diagram. B. Figure 6.22 Correct versions of the ER diagram of figure 6.21. Since relationship instances must be uniquely identified by the participating entities, student and section. One solution to the problem depicted in figure 6.21c, shown in figure 6.22a, is to model assignment as a weak entity identified by section, and to add a relationship marks in between assignment and student. The relationship would have an attribute marks. An alternative solution, shown in figure 6.22d, is to use a multivalued composite attribute assignment marks to takes, where assignment marks component attributes assignment and marks. Modeling an assignment as a weak entity is preferable in this case, since it allows recording other information about the assignment, such as maximum marks or deadlines. When honor diagram becomes too big to draw in a single piece, it makes sense to break it up into pieces, each showing part of their model. When doing so, you may need to depict an entity set in more than one page. As discussed in section 6.2.2, attributes of the entity set should be shown only once, in its first occurrence. Subsequent occurrences of the entity set should be shown without any attributes, to avoid repeating the same information at multiple places, which may lead to inconsistency. 6.9.2 Use of entity sets versus attributes. Consider the entity set instructor with the additional attribute phony number, figure 6.23a. It can be argued that a phone is an entity in its own right with attributes phone. 282 Chapter 6 Database Design Using the ER Model. Instructor ID Name Salary Phone _ Number Instructor ID Name Salary Phone _ Number Location INST _ Phone A, B, Figure 6.23 Alternatives for adding finito the instructor entity set. Number and location. The location may be the office or home where the phone is located, with mobile, cell, phones perhaps represented by the value mobile. If we take this point of view, we do not add the attribute phony number to the instructor. Rather, we create a phone entity set with attribute as phony number and location. A relationship set inst phone, denoting the association between instructors and the phones that they have. This alternative is shown in figure 6.23b. What, then, is the main difference between these two definitions of an instructor? Treating a phone as an attribute phony number implies that instructors have precisely one phone number each. Treating a phone as an entity phone permits instructors to have several phone numbers, including 0, associated with them. However, we could instead easily define phony number as a multivalued attribute to allow multiple phones per instructor. The main difference then is that treating a phone as an entity better models a situation where one may want to keep extra information about a phone, such as its location, or its type, mobile IP phone or plain old phone, or all who share the phone. Thus, treating phone as an entity is more general than treating it as an attribute and is appropriate when the generality may be useful. In contrast, it would not be appropriate to treat the attribute name of an instructor as an entity. It is difficult to argue that name is an entity in its own right, in contrast to the phone. Thus, it is appropriate to have a name as an attribute of the instructor entity set. Two natural questions thus arise: what constitutes an attribute, and what constitutes an entity set? Unfortunately, there are no simple answers. The distinctions mainly depend on the structure of the real-world enterprise being modeled and on the semantics associated with the attribute in question. 6.9.3 Use of entity sets versus relationship sets. It is not always clear whether an object is best expressed by an entity set or a relationship set. In figure 6.15, we used the Thetakis relationship set to model the situation where a 6.9 Entity Relationship Design Issues 283 Section _reg Student _reg Registration, Section SEC _ID Semester Year Student ID Name Taught _cred Figure 6.24 Replacement of Thetakis by Registration and two relationship sets. Student takes a section of a course. An alternative is to imagine that there is a course registration record for each course that each student takes. Then, we have an entity set to represent the course registration record. Let us call that entity registration. Each registration entity is related to exactly one student and to exactly one section, so we have two relationship sets, one to relate course registration records to students and one to relate course registration records to sections. In figure 6.24, we show the entity set section and student from figure 6.15 with Thetakis relationship set replaced by one entity set and two relationship sets, registration, the entity set representing course registration records. Section reg, the relationship set relating registration and course. Student reg, the relationship set relating registration and student. Note that we use double lines to indicate total participation by registration entities. Both the approach of figure 6.15 and that of figure 6.24 accurately represent the university's information, but the use of Thetakis is more compact and probably preferable. However, if the registrar's office associates other information with a course registration record, it might be best to make it an entity in its own right. One possible guideline in determining whether to use an entity set or a relationship set is to designate a relationship set to describe an action that occurs between entities. This approach can also be useful in deciding whether certain attributes may be more appropriately expressed as relationships. 6.9.4 Binary versus Nary relationship sets. Relationships in databases are often binary. Some relationships that appear to be non-binary could actually be better represented by several binary relationships. For instance, one could create a ternary relationship parent, relating a child to his/her mother and father. However, such a relationship could also be represented by two binary relationships mother and father, relating a child to his/her mother and father separately. Using 284 Chapter 6 Database Design. Using the ER model, the two relationships mother and father provides us with a record of a child's mother. Even if we are not aware of the father's identity, a null value would be required if the ternary relationship parent were used. Using binary relationship sets is preferable in this case. In fact, it is always possible to replace a non-binary, nary, foreign GT2, relationship set by a number of distinct binary relationship sets. For simplicity, consider the abstract ternary, n equals 3, relationship set R, relating entity sets A, B, and C. We replace the relationship set R with an entity set E, and we create three relationship sets as shown in Figure 6.25, RA, a many-to-one relationship set from E to A. RB, a many-to-one relationship set from E to B. RC, a many-to-one relationship set from E to C. EIS required to have total participation in each of RA, RB, and RC. If the relationship set had any attributes, these are assigned to entity set E. Further, a special identifying attribute is created for, since it must be possible to distinguish different entities in an entity set on the basis of their attribute values. For each relationship, AIBICI, in the relationship set R, we create a new entity in the entity set E. Then, in each of the three new relationship sets, we insert a relationship as follows: EIAI, INRA, EIBI, INRB, EICI, INRC. We can generalize this process in a straightforward manner to nary relationship sets. Thus, conceptually, we can restrict their model to include only binary relationship sets. However, this restriction is not always desirable. ARARCABRCRBBEC, A, B, Figure 6.25 Ternary relationship versus three binary relationships. 6.10 Alternative notations for modeling data. 285 6.10 An identifying attribute may have to be created for the entity set created to represent the relationship set. This attribute, along with the extra relationship sets required, increases the complexity of the design and, as we shall see in section 6.7, overall storage requirements. An ARY relationship set shows more clearly that several entities participate in a single relationship. There may not be a way to translate constraints on the ternary relationship into constraints on the binary relationships. For example, consider a constraint that says that RIS many-to-one from A B to OC, that is, each pair of entities from OND BIS associated with at most one entity. This constraint cannot be expressed by using cardinality constraints on the relationship sets RA, RB, and RC. Consider the relationship set Project Guide A in section 6.2.2, relating instructor-student, and project. We cannot directly split Project Guide A into binary relationships between instructor and project and between instructor and student. If we did so, we would be able to record that instructor Katz works on projects OND with students Shankar and Zhang. However, we would not be able to record that Katz works on project with student Shankar and works on project with student Zhang, but does not work on project with Zhang or on project with Shankar. The relationship set Project Guide can be split into binary relationships by creating a new entity set as described above. However, doing so would not be very natural. Alternative notations for modeling data. A diagrammatic representation of the data model of an application is a very important part of designing a database schema. Creation of a database schema requires not only data modeling experts, but also domain experts who know the requirements of the application but may not be familiar with data modeling. An intuitive diagrammatic representation is particularly important since it eases communication of information between these groups of experts. A number of alternative notations for modeling data have been proposed, of which ear diagrams and class diagrams are the most widely used. There is no universal standard for diagram notation, and different books and diagram software use different notations. In the rest of this section, we study some of the alternative ear diagram notations, as well as the class diagram notation. To aid in comparison of our notation with these alternatives, Figure 6.26 summarizes the set of symbols we have used in our diagram notation. 6.10.1 Alternative ER notations. Figure 6.27 indicates some of the alternative ER notations that are widely used. One alternative representation of attributes of entities is to show them in ovals connected. 286 Chapter 6 Database Design using the ER model EA1R EA1 A2 A2.1 A2.2 A3 A4 Entity set relationship set identifying relationship set for weak entity set primary key attributes, simple, A1, composite, A2, and multivalued, A3, derived, A4, RE discriminating attribute of weak entity set total participation of entity set in relationship EA1 RER many-to-many relationship R many-to-one relationship RRLHE one-to-one relationship cardinality limits role E1 ISA, generalization or specialization E3 E2 R name E role indicator E1 E2 E3 E1 E2 E3 disjoint generalization total, disjoint, generalization total. Figure 6.26 Symbols used in their notation. To the box representing the entity, primary key attributes are indicated by underlining them. The above notation is shown at the top of the figure. Relationship attributes can be similarly represented, by connecting the ovals to the diamond representing the relationship. Cardinality constraints on relationships can be indicated in several different ways, as shown in Figure 6.27. In one alternative, shown on the left side of the figure, labels and one on the edges out of the relationship are used for depicting many-to-many, 1. 6.10 Alternative notations for modeling data 287 A2.1 A2.2 Entity set E with simple attribute A1, composite attribute A2, multivalued attribute A3, derived attribute A4, and primary key A1 A2 E3 A4 A1 R many-to-many relationship E1 R E2 E1 asterisk E2 one-to-one relationship RE1 1 times 10 squared E1 R E2 many-to-one relationship RE1 asterisk 1 times 10 squared E1 R E2 E1 participation in R, total, E1, and partial, E2. E1 RE2 total generalization weak entity set generalization ISA Figure 6.27 Alternative ear notations. To one, and many-to-one relationships. The case of one-to-many is symmetric to many-to-one and is not shown. In another alternative notation shown on the right side of Figure 6.27, relationship sets are represented by lines between entity sets, without diamonds, only binary relationships can be modeled thus. Cardinality constraints in such a notation are shown by crowsfoot notation, as in the figure. In a relationship between E1 and 2, crow's feet on both sides indicate a many-to-many relationship, while crow's feet on just the E1 side indicate a many-to-one relationship from E1 to 2. Total participation is specified in this notation by a vertical bar. Note however, that in a relationship between entities E1 and 2, if the participation of E1 in R is total, the vertical bar is placed on the opposite side, adjacent to entity E2. Similarly, partial participation is indicated by using a circle, again on the opposite side. The bottom part of Figure 6.27 shows an alternative representation of generalization, using triangles instead of hollow arrowheads. 288 Chapter 6 Database Design using the ER model. In prior editions of this text up to the 5th edition, we used ovals to represent attributes, with triangles representing generalization, as shown in Figure 6.27. The notation using ovals for attributes and diamonds for relationships is close to the original form of diagrams used by Chen in his paper that introduced the notion of R modeling. That notation is now referred to as Chen's notation. The U.S. National Institute for Standards and Technology defined a standard called IDEF-1XIN 1993. IDEF-1 uses the crowsfoot notation, with vertical bars on the relationship edge to denote total participation and hollow circles to denote partial participation, and it includes other notations that we have not shown. With the growth in the use of Unified Markup Language, UML, described in Section 6.10.2, we have chosen to update our notation to make it closer to the form of UML class diagrams. The connections will become clear in Section 6.10.2. In comparison with our previous notation, our new notation provides a more compact representation of attributes, and it is also closer to the notation supported by Menyer modeling tools, in addition to being closer to the UML class diagram notation. There are a variety of tools for constructing diagrams, each of which has its own notational variants. Some of the tools even provide a choice between several R notation variants. See the Tools section at the end of the chapter for references. One key difference between entity sets in honor diagram and the relation schemas created from such entities is that attributes in the relational schema corresponding to relationships, such as the dep name attribute of instructor, are not shown in the entity set in their diagram. Some data modeling tools allow designers to choose between two views of the same entity, one an entity view without such attributes, and other a relational view with such attributes. 6.10.2 The Unified Modeling Language UML Entity Relationship Diagrams help model the data representation component of a software system. Data representation, however, forms only one part of an overall system design. Other components include models of user interactions with the system, specification of functional modules of the system and their interaction, etc. The Unified Modeling Language, UML, is a standard developed under the auspices of the Object Management Group, OMG, for creating specifications of various components of a software system. Some of the parts of UML are: class diagram. A class diagram is similar to honor diagram. Later in this section we illustrate a few features of class diagrams and how they relate to diagrams. Use case diagram. Use case diagrams show the interaction between users and the system, in particular the steps of tasks that users perform, such as withdrawing money or registering for a course. Activity diagram. Activity diagrams depict the flow of tasks between various components of a system. 6.10 Alternative Notations for Modeling Data 289 Implementation Diagram. Implementation diagrams show the system components and their interconnections, both at the software component level and the hardware component level. We do not attempt to provide detailed coverage of the different parts of UML. Instead we illustrate some features of that part of UML that relates to data modeling through examples. See the further reading section at the end of the chapter for references on UML. Figure 6.28 shows several diagram constructs and their equivalent UML class diagram constructs. We describe these constructs below. UML actually models objects, whereas R models entities. Objects are like entities, and have attributes, but additionally provide a set of functions, called methods, that can be invoked to compute values on the basis of attributes of the objects, or to update the object itself. Class diagrams can depict methods in addition to attributes. We cover objects in Section 8.2. UML does not support composite or multivalued attributes, and derived attributes are equivalent to methods that take no parameters. Since classes support encapsulation, UML allows attributes and methods to be prefixed with a plus, dash, or hashtag, which denote respectively public, private, and protected access. Private attributes can only be used in methods of the class, while protected attributes can be used only in methods of the class and its subclasses. These should be familiar to anyone who knows Java, C++, or C#. In UML terminology, relationship sets are referred to as associations. We shall refer to them as relationship sets for consistency with their terminology. We represent binary relationship sets in UML by just drawing a line connecting the entity sets. We write the relationship set name adjacent to the line. We may also specify the role played by an entity set in a relationship set by writing the role name on the line, adjacent to the entity set. Alternatively, we may write the relationship set name in a box, along with attributes of the relationship set, and connect the box by a dotted line to the line depicting the relationship set. This box can then be treated as an entity set, in the same way as an aggregation INR diagrams, and can participate in relationships with other entity sets. Since UML version 1.3 UML supports non-binary relationships, using the same diamond notation used INR diagrams. Non-binary relationships could not be directly represented in earlier versions of UML. They had to be converted to binary relationships by the technique we have seen earlier in section 6.9.4. allows the diamond notation to be used even for binary relationships, but most designers use the line notation. Cardinality constraints are specified in UML the same way as INR diagrams, in the form L. H, where L denotes the minimum nth maximum number of relationships an entity can participate in. However, you should be aware that the positioning of the constraints is exactly the reverse of the positioning of constraints INR diagrams, as shown in figure 6.28. The constraint 0 on the 2 side and 0. 1 on the E1 side means that each E2 entity can participate in at most one relationship, whereas each E1 entity can participate in many relationships. In other words, the relationship is many to one from E2 to 1. Chapter 6 Database Design using the ER model. ER diagram notation. EA1 M10 entity with attributes, simple, composite, multivalued, derived, equivalent in UML. EA1 plus M10 class with simple attributes and methods, attribute prefixes, plus equals public, equals private, hashtag equals protected, RE1 role 1 role 2 E2 binary relationship E1 role 1 R role 2 E2 A1 RE1 role 1 role 2 E2 relationship attributes RA1 role 2 E1 role 1 E2 E3 RE1 RE1 0 asterisk 0 1 E2 E2 cardinality constraints NARE relationships E1 0 underscore 1 0 underscore asterisk E2 RE2 RE1 E3 E1 E1 overlapping E3 E2 generalization E3 E2 E1 E2 E3 E1 disjoint E2 E3 disjoint generalization RE2 E1 weak entity E1 E2 composition. Figure 6.28 symbols used in the UML class diagram notation. Single values such as 1 or may be written on edges. The single value 1 on an edge is treated as equivalent to 1. 1, while is equivalent to 0. UML supports generalization. The notation is basically the same as in AR notation, including the representation of disjoint and overlapping generalizations. UML class diagrams include several other notations that approximately correspond to their notations we have seen. A line between two entity sets with a small shaded diamond at one end in UML specifies composition in UML. The composition relationship between E2 and 1 in figure 6.28 indicates that E2 is existence dependent 1-1. This is roughly equivalent to denoting 2 as a weak entity set that is existence. 6.11 Other aspects of database design. 291 6.11 Dependent on the identifying entity set E1. The term aggregation in UML denotes a variant of composition where E2 is contained in E1 but may exist independently, and it is denoted using a small hollow diamond. UML class diagrams also provide notations to represent object-oriented language features such as interfaces. See the further reading section for more information on UML class diagrams. Other aspects of database design are extensive discussion of schema design in this chapter may create the false impression that schema design is the only component of a database design. There are indeed several other considerations that we address more fully in subsequent chapters, and survey briefly here. 6.11.1 Functional requirements. All enterprises have rules on what kinds of functionality are to be supported by an enterprise application. These could include transactions that update the data, as well as queries to view data in a desired fashion. In addition to planning the functionality, designers have to plan the interfaces to be built to support the functionality. Not all users are authorized to view all data, or to perform all transactions. An authorization mechanism is very important for any enterprise application. Such authorization could be at the level of the database, using database authorization features. But it could also be at the level of higher-level functionality or interfaces, specifying who can use which functions/interfaces. 6.11.2 Data Flow. Workflow database applications are often part of a larger enterprise application that interacts not only with the database system but also with various specialized applications. As an example, consider a travel expense report. It is created by an employee returning from a business trip, possibly by means of a special software package, and is subsequently routed to the employee's manager, perhaps other higher-level managers, and eventually to the accounting department for payment, at which point it interacts with the enterprise's accounting information systems. The term workflow refers to the combination of data and tasks involved in processes like those of the preceding examples. Workflows interact with the database system as they move among users, and users perform their tasks on the workflow. In addition to the data on which workflows operate, the database may store data about the workflow itself, including the tasks making up a workflow and how they are to be routed among users. Workflows thus specify a series of queries and updates to the database that may be taken into account as part of the database design process. Put in other terms, modeling the 292 Chapter 6 Database Design using the ER model enterprise requires us not only to understand the semantics of the data but also the business processes that use those data. 6.11.3 Schema Evolution. Database design is usually not a one-time activity. The needs of an organization evolve continually, and the data that it needs to store also evolve correspondingly. During the initial database design phases, or during the development of an application, the database designer may realize that changes are required at the conceptual, logical, or physical schema levels. Changes in the schema can affect all aspects of the database application. A good database design anticipates future needs of an organization and ensures that the schema requires minimal changes as the needs evolve. It is important to distinguish between fundamental constraints that are expected to be permanent and constraints that are anticipated to change. For example, the constraint that an instructor ID identify a unique instructor is fundamental. On the other hand, a university may have a policy that an instructor can have only one department, which may change at a later date if joint appointments are allowed. A database design that only allows one department per instructor might require major changes if joint appointments are allowed. Such joint appointments can be represented by adding an extra relationship without modifying the instructor relation, as long as each instructor has only one primary department affiliation. A policy change that allows more than one primary affiliation may require a larger change in the database design. A good design should account not only for current policies, but should also avoid or minimize the need for modifications due to changes that are anticipated or have a reasonable chance of happening. Finally, it is worth noting that database design is a human-oriented activity in two senses. The end users of the system are people, even if an application sits between the database and the end users, and the database designer needs to interact extensively with experts in the application domain to understand the data requirements of the application. All of the people involved with the data have needs and preferences that should be taken into account in order for a database design and deployment to succeed within the enterprise. 6.12 Summary. Database design mainly involves the design of the database schema. The entity relationship, ER, data model is a widely used data model for database design. It provides a convenient graphical representation to view data, relationships, and constraints. The ER model is intended primarily for the database design process. It was developed to facilitate database design by allowing the specification of an enterprise schema. Such a schema represents the overall logical structure of the database. This overall structure can be expressed graphically by honor diagram. Review terms. 293 An entity is an object that exists in the real world and is distinguishable from other objects. We express the distinction by associating with each entity a set of attributes that describes the object. A relationship is an association among several entities. A relationship set is a collection of relationships of the same type, and an entity set is a collection of entities of the same type. The terms superkey, candidate key, and primary key apply to entity and relationship sets as they do for relation schemas. Identifying the primary key of a relationship set requires some care, since it is composed of attributes from one or more of the related entity sets. Mapping cardinalities express the number of entities to which another entity can be associated via a relationship set. An entity set that does not have sufficient attributes to form a primary key is termed a weak entity set. An entity set that has a primary key is termed a strong entity set. The various features of their model offer the database designer numerous choices in how to best represent the enterprise being modeled. Concepts and objects may, in certain cases, be represented by entities, relationships, or attributes. Aspects of the overall structure of the enterprise may be best described by using weak entity sets, generalization, specialization, or aggregation. Often, the designer must weigh the merits of a simple, compact model versus those of a more precise, but more complex one. A database design specified by honor diagram can be represented by a collection of relation schemas. For each entity set and for each relationship set in the database, there is a unique relation schema that is assigned the name of the corresponding entity set or relationship set. This forms the basis for deriving a relational database design from honor diagram. Specialization and generalization define a containment relationship between a higher-level entity set and one or more lower-level entity sets. Specialization is the result of taking a subset of a higher-level entity set to form a lower-level entity set. Generalization is the result of taking the union of two or more disjoint, lower-level, entity sets to produce a higher-level entity set. The attributes of higher-level entity sets are inherited by lower-level entity sets. Aggregation is an abstraction in which relationship sets, along with their associated entity sets, are treated as higher-level entity sets, and can participate in relationships. Care must be taken in your design. There are a number of common mistakes to avoid. Also, there are choices among the use of entity sets, relationship sets, and 294 Chapter 6 Database Design using the ER model attributes in representing aspects of the enterprise whose correctness may depend on subtle details specific to the enterprise. UML is a popular modeling language. UML class diagrams are widely used for modeling classes, as well as for general-purpose data modeling. Review terms: design process, degree, conceptual design, degree, logical design, degree, physical design, entity relationship, data model, entity and entity set, degree, simple and composite attributes, degree, single-valued and multi-valued attributes, degree, derived attribute key, degree, superkey, degree, candidate key, degree, primary key, relationship and relationship set, degree, binary relationship set, degree, degree of relationship set, degree, descriptive attributes, degree, superkey, candidate key, and primary key, degree, role, degree, recursive relationship set, diagram mapping. Cardinality, degree, one-to-one relationship, degree, one-to-many relationship, degree, many-to-one relationship, degree, many-to-many relationship, total and partial participation, weak entity sets and strong entity sets, degree, discriminator attributes, degree, identifying relationship, specialization and generalization, aggregation, design choices, united modeling language,